Hello, I'm George Kelesidis, and here I'm going to talk about the light absorption dynamics of brown carbon particles during wood combustion and pyrolysis. Wood combustion has been used since the ancient times for heat and energy generation. Nowadays, wood combustion has attracted significant scientific and industrial interest, with large biomass combustion power plants being built all over the world. This is because wood combustion can assist the reduction of CO2 and greenhouse gas emissions, even though it still releases significant concentrations of hazardous particulate matter. However, the increasing frequency of wildfires has drawn attention to the environmental and health impacts of particulate matter emissions from wood combustion. In fact, these emissions affect now millions of people that live in metropolitan areas. For example, in summer 2023, strong winds brought rather fresh wildfire smoke from Quebec in Canada all the way to northeast United States. At the campus of Rutgers University, which is located just a few miles away from New York City, we went outdoors to characterize these emissions. So at the peak of this wildfire incident, we measured a particulate matter mass concentration of about 300 micrograms per cubic meter. For your information, this mass concentration is about 20 times larger than the 24-hour exposure limit that is set by the World Health Organization. Now let's look at these emissions under the microscope. Wildfire smoke contains 1 to 5% of soot nanoparticles that are commonly identified by atmospheric scientists as elemental carbon. It's well known that soot nanoparticles coagulate to form fractal-like agglomerates, such as the one that you can see in this microscopy image. These soot agglomerates absorb strongly light, and their light absorption is typically quantified by the mass absorption cross-section, which indicates essentially the light absorbed by a single soot agglomerate. We recently derived the mass absorption cross-section of soot, accounting for its realistic agglomerate structure, and we interfaced it with a global climate model to derive the direct radiative forcing that is induced by soot agglomerates at different regions of the world. Now, wildfire smoke contains also 95 to 99% of organic and brown carbon particles. The focus of my presentation today will be on brown carbon. Brown carbon refers to semi- and non-volatile spherical particles, such as those that you can see in this microscopy image over here, which actually comes from a real wildfire. Unlike volatile organic carbon, brown carbon actually absorbs slightly light, and thus it contributes to climate change. However, as you can see in this figure over here, the light absorption from brown carbon that has been emitted from wildfires is much smaller compared to the light absorption of mature soot that is emitted, for example, from diesel engines. However, you may notice over here that there is a large uncertainty regarding the mass absorption cross-section of brown carbon. This uncertainty can be attributed, at least partly, to the large variation of the wood combustion conditions during a wildfire. So here we are going to connect the wood combustion conditions to the light absorption of brown carbon to assist global climate models to estimate accurately the climate impact of brown carbon emissions from wood combustion. The experimental part of this work was largely done by our postdoctoral researcher, Dr. Konstantinos Moularas, who used this tube furnace to combust pinewood powder. In particular, a crucible containing 50 milligrams of pinewood powder was placed in the middle of this tube furnace in nitrogen atmosphere that contained different oxygen concentrations. The oxygen concentration was varied from 0 to 20% to cover a large range of combustion conditions that are present during a wildfire. At the same time, the temperature was increased up to 400 degrees Celsius. The gaseous emissions from pinewood combustion were monitored using analyzers for carbon monoxide and volatile organic compounds. The emitted brown carbon particles were thermally denuded and then diluted using a rotating disk, to avoid any coagulation in the sampling line. The total number concentration as well as the mobility size distribution of brown carbon were monitored in real time using a scanning mobility particle size. Brown carbon particles were also directed into a compact cascade impactor. There, brown carbon particles were size fractionated based on their aerodynamic diameter, and they were deposited on filters to characterize their mass concentration and elemental carbon content. The size selected brown carbon particles that had an aerodynamic diameter smaller than 2.5 micrometers were directed into a photo extinction meter. There, we measured their absorption coefficient at a wavelength of 405 nanometers. So, on the y-axis, at the right-hand side of this plot, I'm presenting you the furnace temperature that has been obtained as a function of the residence time shown on the x-axis. The temperature is increased at a rate of 20 degrees per minute. So we reach the 400 degrees at about 20 minutes, and then we hold the temperature constant for about another 20 minutes. On the y-axis, shown on the left-hand side of this plot, I'm presenting you the total number concentration of brown carbon that has been obtained as a function of the residence time during pinewood combustion with air. The shaded area over here quantifies the variability of our measurements. So as you can see, in the first few minutes, the total number concentration is very low. It's close to the detection limit of our instrument. At about 15 minutes though, the furnace reaches a temperature of about 300 degrees. So the cellulose that makes up the pinewood powder starts to decompose. So the total number concentration increases by 3 to 4 orders of magnitude within about 5 minutes. Of course, as the residence time increases, the cellulose is gradually consumed and the number concentration of brown carbon decreases. So after 30 minutes from the start of our experiment, the brown carbon emissions stop. So next, we are going to focus on the brown carbon particles that were emitted at the residence time that we attained the peak total number concentration. So on the y-axis here, I'm presenting you the number concentration measured as a function of the mobility diameter of brown carbon particles emitted from pinewood combustion with air. As you can clearly see in this figure, the brown carbon size distribution is bi-modal. The first mode contains particles with a mean diameter of about 30 nanometers, while the second mode contains particles with a mean diameter of about 80 nanometers. And about 70% of all brown carbon particles are located in the first mode of this size distribution. Now, we also obtained the mobility size distribution for brown carbon particles emitted from pinewood combustion with nitrogen containing 10% of oxygen and even 0% of oxygen. The latter conditions correspond to wood pyrolysis. As you can see, at all oxygen concentrations, the brown carbon size distribution is bi-modal. However, as we increase the oxygen concentration, the oxidation of small brown carbon particles is enhanced, and it reduces their mobility diameter as well as their number concentration. So that way, the fraction of large brown carbon particles that are located in the second mode increases from 5 to about 30%. So we recently derived a lattice Monte Carlo model to describe the oxidation dynamics of carbonaceous nanoparticles such as soot, carbon black, and brown carbon. If you are interested, you can pass by our poster on July 23rd, or you can read our recent publication in Carbon. So, as I mentioned earlier on, we used this cascade impactor to measure the mass concentration of brown carbon. For example, during pinewood combustion with air, we obtained a mass concentration of brown carbon particles with an aerodynamic diameter smaller than 2.5 micrometers of about 23 milligrams per cubic meter. As we decrease the oxygen concentration in the nitrogen atmosphere, the mass concentration increases up to 40 milligrams per cubic meter. So increasing the oxygen concentration enhances the brown carbon oxidation and reduces its mass concentration by 43%. This large reduction is actually consistent with the reduction of the volume fraction and number concentration of soot from ethylene and jet fuel combustion using large oxygen concentration. So the size-selected brown carbon particles that are exiting the impactor are directed to a photo extinction meter to measure their average absorption coefficient. And by dividing the absorption coefficient by the measured mass concentration, we can obtain the mass absorption cross-section of brown carbon. So brown carbon particles emitted from pinewood combustion with air have a mass absorption cross-section of about 0.3 square meters per gram. As we decrease the oxygen concentration in the nitrogen atmosphere to 10 and 0%, you can see that the light absorption of brown carbon is reduced by about 75%. These large variations of the brown carbon light absorption are often attributed to the presence of elemental carbon or soot. However, the elemental carbon content was negligible for all brown carbon samples that were analyzed here. So the large reduction of the brown carbon mass absorption cross-section with a decreasing oxygen concentration can be attributed to the increase of the number concentration of small brown carbon particles. To corroborate this hypothesis, we modified slightly our experimental setup. So here we focus on the light absorption of brown carbon emitted from pinewood combustion with air. However, we included here an additional stage in our impactor. So that way we were able to size-select brown carbon particles that had an aerodynamic diameter smaller than 0.1 micrometers. That way we obtained a mass absorption cross-section of about 0.07 square meters per gram for the smallest size fraction of brown carbon. And based on the light absorption of the PM2.5 and the PM0.1 size fractions of brown carbon, we can infer the light absorption of particles that have an aerodynamic diameter between 0.1 and 2.5 micrometers. As you can see here, the light absorption of the large size fraction of brown carbon is about 5 times larger than the light absorption of the small size fraction of brown carbon. So the brown carbon mass absorption cross-section increases with increasing particle size. And this trend is actually consistent with recent measurements of the soot mass absorption cross-section in different diesel engines and diffusion flames. Most importantly, the mass absorption cross-sections that we measured here for small and large brown carbon particles are in line with the mass absorption cross-sections that have been measured for brown carbon from various wildfires. So the mass absorption cross-sections that we measured over here can be interfaced with global climate models to derive the radiative forcing that is induced from brown carbon emissions emitted from wood combustion. And with this, I would like to come to the conclusions of this work. So here we elucidated the dynamics of brown carbon particles during wood pyrolysis and combustion at controlled temperature and oxygen conditions for the first time to the best of our knowledge. That way we showed that increasing the oxygen concentration in the nitrogen atmosphere of our reactor enhances the oxidation of the small brown carbon particles, and it reduces their number concentration and mobility diameter. Most importantly, we showed here that the light absorption of brown carbon increases with increasing oxygen concentration as well as with increasing particle size. So the mass absorption cross-sections that we derived here for small and large brown carbon particles are in line with those measured for particles emitted from different wildfires. So these mass absorption cross-sections can be interfaced with global climate models to quantify accurately the climate impact of brown carbon emissions from wood combustion. With this, I would like to thank you so much for listening. If you are interested to learn more about this work, please read our recent publication in the Proceedings of the Combustion Institute.